Back in the 1950s or earlier, if you wanted to listen to AM radio, you would need something that was plugged into a good power supply, and it would have an aerial or an antenna sticking out outside somewhere, and you might also have a wire driven into the ground, and that's how you received an AM radio station. Somewhere around the 1950s, there was this material invented called ferrite. This gray material right here, which is kind of a magnetic material that can tolerate high frequency changes in magnetism without turning it into heat. Um, in the 1950s, they invented this material, and then they were able to take wire and wrap it around. This is a wire, just a coil of wire, and now this would replace the aerial antenna in a radio. So this short little piece of metal with a loop wrapped around it now makes a radio portable. So then in the 60s, transistors became common, and so the pocket radio became a reality. You could have a transistorized radio that was very small. Um, so this was a marvelous invention. Now, when this was invented, there was a theory why it operates and how it operates. That theory existed for years, and people developed an equation. One of the equations they developed was how is the radiative resistance of this coil affected by the length of this material, its area cross section, how many turns are around it, and then also the magnetic permissivity, or however you I'm not sure the correct term. It's like a magnetic conductance. It's called mu. How does that affect it? So somebody came up with an equation based on a theory called um, demagnetization, and this is the equation they came up with, that R equals this fancy equation. So the numbers that you're plugging into it are, how many turns, how much area is the cross section, the length of the stick, and the mu. Okay, so for 50 years, this equation was the equation. These components of the equation were pretty much figured out through a process of dimensional analysis. And then these little constants out front here, these multipliers, were determined experimentally. Well, for 50 years, people were using that, and it was giving them terrible results. So here, I'll just show you. I'll show you some of the graphs. Based on the theory of demagnetization, the permeability of the coil would follow this curve up here, based on the theory and that equation I showed you. But experimentally, this is the correct answer. So for 50 years, people didn't have a good equation. Then some guy came around and he developed a new theory of this antenna. He called it a magnetic dipole. So he started with a whole different concept of how we should consider this as operating. So he had a different set of variables that he plugged in, and he came out with a different equation, an improved equation. Okay, the improved equation looks very similar to the original equation. Let's see if we can put them side by side. See, the only difference here, they almost look almost identical. So the bad formula has 31,200 multiplying something. The new one's got the same 31,200 multiplying something. So here you have something called mu f, and then down here you have something called g rod. But the rest of the equation is the same. If you look at the, the far right, you got that number of terms times the area squared. Same thing over here. It's the number of terms and the area squared. So it's a very similar equation. You say, well, what kind of difference does that make? Well, when it was all said and done, when this guy came up with a new theory, how it operates, and I'll show you real quick. Now, this is something that may not interest you, but I'm just showing you something that people, it's not uncommon for engineers and scientists to have wrong equations because they have a wrong theory, they have a wrong starting point. But then somebody else comes along, a smarter person, and they have a better starting point. They understand it better, and so they end up with a mathematical formula that works better. So look at this graph. So this is the signal ratio. So we want to figure out the signal ratio for this antenna when it's exposed to a certain amount of electromagnetic radiation from a broadcast tower. Okay. So this is what the old formula would have predicted. Now that's as you lengthen the rod. The longer this rod becomes, see this rod? You should get this kind of improvement in the signal. That's what they were saying with the old formulation. But in reality, this is both a graph of the actual measurement and then also the theory predicting it, the new theory. So you see the new theory as it predicts it and the actual measurement are almost completely on top of each other. So using the process, using first a correct theory and understanding, you can come up with the right variables to put into an equation. They put the wrong variables in initially. They thought one thing was important when it was really something else. And then through experimentation, you can develop constants to multiply things by. So I know that we're working on a pendulum and it's a completely different problem. But in one hand, it is really, again, the same problem all over again. Being able to understand something theoretically and then being able to create the correct equation that predict its results. These numbers here, these multipliers were probably determined experimentally. But these over here were probably determined through the dimensional analysis concept, where a person developed a new theory and then based on that theory came up with a different equation. And now when you're engineering using something like this for radio reception, you have a better idea of how it's going to perform in the circuit. I just thought you should see an example of something.